Hey, nice of you guys to join us today. Well, today we have the following problem, which is equilibrium reaction at an equilibrium constant pressure of 3.16. And in this following equilibrium reaction, we have the equation 2PO4 in equilibrium with 2PO3 plus O2. And things to know here are it's at 273 Kelvin in a 1.0 liter container, and the weight of the substances are 4.56 grams of PO4, 6.54 grams of 2PO3, and 1.32 grams of O2. And the first part of the question asks, in what direction will a net change occur? Second part of the question asks, what will be the partial pressures? Now, starting off with the first one, in order to find out what direction a net change will occur, we're going to have to use this guy over here, and we're going to have to compare it to the Q constant. Pretty sure you all remember that. But we all know, since it's a pressure problem and not a chemical equilibrium problem, we're going to have to find the pressures of these. So we have the mass, so we're going to have to convert this first to moles. So convert this 1 mole over molecular weight, equals 0.48. This one we have and we're using the molecular weight. We're using a little bit of stoichiometry. Okay. Now, if this was a regular chemical equation problem, we would just use the concentrations and plug them into the Q. But here we have a pressure problem. So what we're going to have to do now is use the equation PV equals nRT to find out pressure. So you can derive that divided by T, so we get P equals nRT over V. So we have the N, which will be our concentrations right here, molarity, and we know R and we know T, and we also know volume. So let's plug those into the Q constant. Let's plug those into this equation here. So for PO4. So that's for PO4. So I'm gonna have to erase this here. Sorry about that, guys. So for P03, we have concentration of 0.0828 times 0.8206 all over 1 liter. And from that we will get 1.85810. So box this in. Also box this in. Now for our O2, we have concentration of 0.0413 times 0.0826 times 273, all over. Exactly. And from there we get 0.925810. So now that we have all the pressures, we can plug it into our Q constant. We'll plug it in right about here. So from Q, we have all and as you see, I squared this over here because of the PO4, the coefficient at the PO4. And squared this here because of the coefficient right here at the PO3. And from here we will get 2.71. Okay. So what we're going to do now is use this. This is our Q value. So what we're going to do, as I explained earlier, we would need this, and now we're going to compare this to each other. So a trick I like to use when I was in Chem 2B was I would align all the K's, and I would do one where it's greater than and less than Q. Okay? And we'll plug in, and then just leave that up here for now. And we'll plug in our K, which is 3.16, and then we'll bring our Q, which is 2.71. Now the 3.16 is greater than 2.71. And with this here, what we're going to do is, I just like to draw a line through here, draw a line through here. This always reminds me of which way the reaction will go, depending on the concentration, or as we have here, the pressure. So what we have here is that our K is actually, Kp is actually greater than our Q. So from looking at this, we know that the reaction will be moving forward. And if K was less than Q, the reaction will be in the reverse order. And that concludes it for this problem. So for part B, the question is, what will be the partial pressures of each of the species? Well, we know from our K equilibrium constant, we can derive an ice table. We can derive an ice table using the pressures that we found from part A. And what we will get over here is 2PO4 in equilibrium with 2PO3 plus O2. And our concentrations for each respectively. 7. And since from part A we found out that the reaction is going forward, we know the concentration is going to move this way. And since our coefficient is 2, we would from these, we can plug this in to our equilibrium problem, in which I already have done for you. We know that it's reactants over products. So this would stand for PO3, and we would square because of our coefficient, our O2, and didn't have a coefficient, so it would be just plus X, and also 1.08 for our reactants. So from this equation, we can derive the X using, also there's we can use the quadratic equation. And if you use the quadratic equation, what you'll get for X, you'll get 0.0218. So if you solve this out, and then at the end, you put in the standard form, you can use the quadratic equation, and you'll get your X. And what you want to do with this X is plug them in to the equilibrium table, which would be the X here, and X here. So if you plug this value into the X's here, you will get a pressure of 1.04 atm. That would be our pressure for PO4. And you'll get 1.89 atm for our PO3. And for our O2, you'll get 1.47 atm. And there you have it. Those are each of the partial pressures of each of the species. And there you have it. Thank you.